we are looking at projections. Okay. So, just want to make one remark. The other day I said this P1 plus P2 is a projection. If I only say P1 is orthogonal to P2, I also wrote P1 minimum, P2 equal, this is equivalent to this. Okay? This is not correct, but Bhaskar pointed out. But what is correct is this. This is true. If and only if P1, P2 equal to 0. Okay. So product is 0. Only then P1 plus P2 becomes a projection. So anyway. So replacing subsets by subspaces, you get these projections as our events. Okay, so these are the events, and the probabilities are described through a row. So the row gives you the measure. Okay, so probability of an event, a projection, say P is so probability of under row. Probability of P is trace row. So P belonging to P of H. So that is the understanding we have. For any projection P, the probability of that event occurring, okay, is trace row P. Now row, what is row? If you remember, row is a positive operator with the trace of row equal to 1. Okay? And the special one is the kind where you have pure states. So here rho is the projection onto a rank 1 projection. Projection onto a span of some vector. I take a unit vector u. So this is the projection onto the space spanned by u, the one-dimensional space spanned by u. So in this case, trace row P just becomes, we apply P on vector u and take inner product u. It's just that. Okay. And P is positive and it is between 0 and identity. So that means this is a number between 0 and 1. Okay. So the probability, it's a probability, so it should always be between 0 and 1. Okay. And a general case, a row is of this kind. It is a convex combination of this kind of rank ones. It is compact. The trace is 1, so you can do the spectral decomposition for row, and so it will have a decomposition like this. Okay, where these pj's are greater than or equal to 0, and the summation is 1. Okay. So it's a convex combination. So maybe an infinite convex combination of this. Okay, of such things.
These are not the eigens.
These are the eigen projections. These are the eigenvalues of rho. Yeah. This is the decomposition for rho. Rho is positive on trace 1, so that means in some basis, in this basis of uj's, you can write rho as like this, P1, P2, P3, etc. Okay. So it is a probability vector, P1, P2, P3, adding up to identity.
Plus some zeros.
Yeah.
Plus some zeros.
Now, if it is, see, if H is finite dimension, it will go up to Pn. Okay, it is depends upon the dimension of H. Otherwise, it can be an infinite sequence.
It can be.
Yeah.
But PJs are non-zero. They are non-negative, which means zeros are right.
Means if you want to include zeros, you can include zeros at the end, no, separately. Okay. It's
Raja, you said that eventually you will go to von Neumann algebras,
Yeah.
but you need traces. Do you restrict to into one factors or something?
It depends upon the context. Okay. Some people do it, but quantum field theory they do talk about type 3. Yeah. So, but this is the sort of basic setup. Then from there are many variations and.
States, normal states.
So these rows are called density matrices or states.
What is the definition of the
once I do this, then it's okay.
Oh, you just assume
It's an
that.
abstract theorem where that this is. But now we will say that we will take only this type. But dimension 2 is very important for this subject of quantum computation or quantum information. They start with dimension equal to 2.
Yes.
They, like the computer, usually we have this 0 and 1. So the same thing, they want to have the binary things. So for that, what they call qubits. So that means dimension of h should be equal to 2. Okay. So here, with this we have then the random variables, which we call them as observables. Okay. So that means x belongs to is an operator where x equal to x star. Okay. Again, you see, I am taking it as a bounded operator, but in general later on it may not even be bounded. It can be unbounded self-adjoint. That is also fine. So now if x has a decomposition, spectral decomposition like this, say aj, pj, j from 1 to n, say, okay. So pj's are projections adding up to identity. They are orthogonal projections. So that is given by pj equal to pj square equal to pj star. They are orthogonal projection. Pj is orthogonal to pk for k not equal to k. So this is then the spectral decomposition of x. Okay. So of course, then if I want to say that this is spectral decomposition, I should also say that aj is not equal to ak for k not equal to k. So they are distinct eigenvalues with corresponding eigenprojections. So if you have it that way, then I say that probability that x takes the value aj is trace rho pj. Okay. So under rho, probability that x equal to aj is trace rho. Okay. So this is the understanding we have. Okay. Which if rho is a pure state, then it just this pj. Okay. And so this is if you have x takes finite number of values, that is x is a sort of simple random variable. Okay. But the general case, what happens in the general case, x will have a spectral measure, and so that's the general case. You have something called a spectral measure for x. X, and so probability that then x belongs to a D, okay, is trace rho E of B, where B is a Borel subset of R. So that would be the general thing. Here x takes only these values, a1, a2, a. Okay. Anyway, let us concentrate now on this kind of things. So, okay. So what I do next? So once we talk about random variables, then we talk about moments, expectation, variance, and things like that. Okay. So we can do the same thing here. So. So what is expectation of x under this state rho? The expectation of x is a definition. These are the values with corresponding probabilities. So values and probabilities you multiply and add. That is the expectation, right? So expectation of x is summation aj trace. These are the probabilities. So you multiply and add. Okay? But these are just numbers, so I can put that inside, and trace is linear, so I can take that inside. So it becomes trace about summation aj pj. But this summation is just x. So it is just trace rho x. expectation of x is trace rho x. Okay, and that is you should compare with this. You see, projection means indicator function, right? The expectation of that is the probability of that, right? Means it's 1 with probability p, 0 with probability means like an event p. It is 1 with probability p equal to trace rho p, and the 0 with 1 minus that. Okay? And the expectation of that is that probability itself. Okay, so that you get trace rho p. Okay, so expectation of x is trace rho x. So now, so this we can define actually this map on whole of B of h. So though here I am taking only self-adjoint things, I can define it, the map x goes to trace rho x.
Will x be integral? X will be integral x dp kind of thing.
It is the expectation, right? It is basically that. So that's why many people say, right, in non-commutative theory, the trace replaces the expectation of the integration. Okay, trace replaces. So x goes to trace rho x. So this is the expectation map. Okay. So expectation of any random variable x or any observable x is trace rho x. Okay. There is one small technical thing. So you ask whether any state on B of h is of this kind. A state, if you see, do C-star algebras, the state means it's a positive linear functional which sends identity to 1. Okay, the state on unitary C-star algebras are positive linear functionals which send identity to 1. So you ask whether all states look like this. The answer is no, because you need some continuity. Okay, not just the usual. Okay, on B of h, you can have this kind of states which is 0 on all compact operators, and it's just 1 on identity. So you can. So this is just my side remark. Like something, if you are working on this field, then you should know. Like on B of h, I can take a quotient with compacts. So that is known as the Kalkin algebra. So you can take a state on that. So if you take a state on that, so that means this is a map from here to complex numbers. Okay, which sends is positive, sending identity to 1. But I can compose with this with the quotient map from B of h. So then this composition you see a state here which sends all compact operators to 0.
So what is k? Sorry, I was
K is the combination of compact operators. Quotienting by compact operators, that is known as the Kalkin algebra. So there are states, okay, which sends all compact operators to 0 but identity to 1. So this one will not do that. So this is a special state. This collection of states are the so-called normal states. So it corresponds to that countable additivity. If you assume countable additivity there on projections, then these are the ones which you get. Okay, so these are sort of bad ones. So, but there are such states, but we don't look at them. Okay, we look at only normal states, states of this kind. So I will ignore these things. All normal states look like this. Now, this is the expectation, right? So I'll write expectation of, I have written already, trace rho x. Now, what is the second moment? Of x square. You can do the same thing with summation aj square, right? But it is trace rho x square. X square has this decomposed. Summation aj square pj, because these pj's are mutually orthogonal. Get that. Okay, so either x square itself is an observable expectation of that is rho x square. So you may also compute it like this. Okay. So right, it comes from the spectral theory. For x as this decomposition summation aj pj, in x square as the decomposition summation aj square pj. Okay. It is just that in this may not be the spectral decomposition of x square, because some of the aj squares might be same. Right? They may not be distinct. Aj and minus aj would give you the same. But this is a regular thing what happens in probability theory also. When you compute expectation of x square, you may compute it using the distribution of x or using the distribution of x square. Okay, either way. So anyway, so expectation of the second moment of x square is trace rho x square. So I can do it generally for m greater than or equal to 0. Expectation of x to the power m is trace rho x to the power. Right? So that means I can compute all the moments like this. Okay? Now I did it for the summation thing. You can do it for the general case also. It's just that the summation gets replaced by integral, but everything else is fine. The same formula works. Okay. So the important thing to note here is that moral of the story, after you do this computation, the moments to compute moments of x, okay, you don't have to know the spectral decomposition of x. It is enough to just compute trace rho x to the power m, right? For that I don't have to know what is this decomposition. I know rho, I know x, then I can compute trace rho x. Then I can multiply x with itself and compute trace rho x square. Okay? So to compute moments x, we need not know the spectral decomposition of x. This is very important because in theory it is fine, but it's very hard to get hold of the spectral decomposition. It's very easy to give examples of self-adjoint operators. Right? You take any bounded operator A, you compute A plus A star, that is self-adjoint. Or you compute A star A, that is positive, and hence self-adjoint. So it's very easy to give examples of self-adjoint operators. But to actually compute the spectral decomposition of that is very hard. But here you can compute all the moments easily. Once you have rho and x, you just have to multiply and take the trace, then you get the moments. Okay?
Can you recover x from the moments?
So that is the next thing I want to say.
Condition then.
Yes. The point is that all the x we are handling here are bounded operators on H. So the spectrum of x, okay, spectrum of x is here within minus norm x to plus norm x. The spectrum of x is a compact set here, in minus norm x to norm x. It is within that, and the spectral measure is supported on this. All the eigenvalues are here within the spectrum, in the spectrum of x, and the spectral measure is supported here. Okay, so that means my measure here, what we are getting here, this is a usual probability measure. So that is supported on the spectrum of x. So in particular in this compact set. So once this is the case, there is a general theory for probability measures which says that if the measure is supported on a compact set, then it is determined by its moments. So in general that is not the case. If you have a random variable or a probability measure which is if the support is not bounded, then you cannot say that. Okay, that with the same moments you can have different distributions. Okay, so the moments need not determine the distribution, but in this case one once I restrict myself to bounded operators on X, then it is good enough to know the moments. So that is what we will do next. Not today, but in the next class. We start with the moments and see. And it is something amazing you should realize. Like I take, say, rho as the pure state like this. Okay. In fact, say let me take the basis vectors E1, T1 in Cn. So you take any n cross n self-adjoint matrix. Okay, 5, 2, 1, 0. Like this, any self-adjoint any symmetric matrix. Look at the, say, the first diagonal entry of x, x square, compute x square, and look at the first diagonal entry. Like that, you can, they form a moment sequence. They are moments of a random variable, which is no way of